If you've ever traveled on a rainy day here in Uganda, you've probably seen it. A heavy vehicle gets completely bogged down in the thick mud, while another manages to push its way through. Why does one get stuck while the other keeps moving? The answer comes down to something we can't see, but we feel every day: a force. A force is simply a push or a pull on an object. And to understand exactly how much pushing or pulling is happening, we measure it in a unit called newtons. Imagine a stalled matatu. The passengers get out and push, but the thick mud pushes back with the exact same amount of force. The result? The van doesn't move a single inch. This diagram illustrates a state of balanced forces. The physical push from the passengers and the mechanical resistance of the mud cancel each other out. Mathematically, the overall push, or the resultant force, is exactly 0 newtons. But then a few more people jump in to help. Now the pushing force grows. It completely overpowers the mud's resistance. Because the forces are no longer equal, we have what is called an unbalanced force. The matatu finally lurches forward. Whether an object stays perfectly still, starts moving, or comes to a sudden stop depends entirely on which invisible push or pull is winning the tug-of-war. Now, let's leave the mud behind and travel to the steep, winding green hills of Kabale. Navigating a heavily loaded boda down these sharp inclines requires immense control, and that control comes directly from a very specific physical force. We call this force friction. Friction happens whenever two surfaces slide past each other, and it always works to oppose that motion. It actively tries to slow things down. Motorcycle tire treads physically interlock with rough road bumps, creating the heavy friction needed to safely stop. But completely smooth tires on a rainy day can't grip. Water sills the tiny road gaps, dropping friction to 0, causing the bike to skid. So friction is a crucial physical grip that keeps us safe. It allows us to walk without slipping and drive without crashing. Another invisible force is at work every time we lift heavy agricultural loads, like hoisting a large sack of beans onto a transport van. In everyday language, we often mix up two very different ideas: mass and weight. Let's separate them. Mass is the actual physical amount of matter stuffed inside that sack. We measure this matter in kilograms. Let's say this particular sack has a mass of 90 kilograms. This graphic shows how that mass interacts with the Earth. Weight is the invisible pull of Earth's gravity acting on that 90-kilogram mass. To find the weight, we multiply the mass by gravity. On Earth, that downward pull creates a weight of 900 newtons. To prove mass never changes, let's try an extreme experiment. Imagine launching that exact same 90-kilogram sack of beans to the International Space Station. In the microgravity of orbit, the amount of matter, the mass, is exactly the same 90 kilograms. But because the Earth is no longer pulling it down, the weight drops to exactly 0 newtons. The sack floats freely. Mass is the physical stuff you are made of. Weight is simply how hard the planet you're standing on is pulling you down. If we look away from these heavy loads and peer into a tiny rain puddle, we find a different scale of forces. Notice how this delicate insect, a pond skater, is standing perfectly still on top of the water without sinking. To see how this works, we have to zoom in to the microscopic level. This diagram shows water molecules. Identical molecules like these fiercely pull toward each other. We call this force of attraction cohesion. The water molecules essentially hug each other tightly. Because the molecules right at the top surface have no water above them, they cohere even more strongly to the ones beside and below them. They form a tight skin. This is a phenomenon we call surface tension, and it acts like a microscopic trampoline for the insect. But this trampoline has a weakness. If you introduce a single drop of soap or oil into the puddle, those impurities immediately break the cohesive bonds. The surface tension snaps, and floating pests like mosquito larvae will instantly sink. On a microscopic scale, a liquid can act like a solid barrier, purely because its molecules refuse to let go of each other. Now look up from that puddle to a towering 50-meter-tall mavule tree. How does a tree that size pull water from its deep roots all the way to its highest leaves without a mechanical pump? It relies on the counterpart to cohesion, known as adhesion. As you can see in this diagram, adhesion is the attraction between molecules of different substances. Notice the blue water molecules aggressively sticking to the vertical walls of the narrow wooden stems inside the tree, curving slightly upwards. This illustrates the principle of capillarity. Whenever the outward pull of adhesion is stronger than the inward pull of cohesion, the liquid will naturally climb up narrow spaces, completely ignoring the downward pull of gravity. We use this exact biological process in our homes. When you light a traditional Tataluba lamp, it is this same adhesive force that draws the kerosene up through the tight threads of the wick to feed the flame. By taking advantage of adhesion, both natural ecosystems and human engineering can move fluids vertically, defying gravity. When we step back and look at the landscape around us, every action, every movement, and every heavy load is governed by the rules we've just explored. The big, visible world of pushing stuck matatus out of the mud or safely braking a boda on a steep hill is ruled by macro-mechanical forces. Meanwhile, the tiny, hidden world of water-walking insects and towering trees is ruled by micromolecular forces. This chart shows how these rules neatly divide into two categories: the mechanical forces, like gravity and friction, and the molecular forces, like cohesion and adhesion. Mastering these concepts provides the tools to calculate weight, manage friction, and understand the molecular bonds that allow us to interact with and navigate our world.